Thanks very much for the intro. It's really exciting to be here. Okay, so I wanted to start off with a story about my friend Andrew. That's him in the picture there. As he says in his page, he didn't want to pay for the larger version, so he got stuck with this tiny little version with a proof on it. This is his picture from his graduation from Columbia, where he did law school. So like many of us, including Tim Urban, one of my favorite bloggers on the web, Andrew suffers from procrastination. So instead of pacing out his workloads like this, he tends to pace them out like this. And when he was in his first year at Columbia doing his JD, found himself in a tricky situation where he just didn't have time to complete his final assignment, which was to read through a bunch of case law and make a decision as to how a judge might opine upon a matter. What Andrew noticed was that he had a tool set at his disposal. So all Columbia law students had, as one of their study tools, a database that had all of the answers that former Columbia students had given to the same question. So in the witching hour at midnight before the assignment was due, he said, well, as opposed to my reading through all of the precedent to make a judgment call on how a judge might opine in this case, how about I just look through the answers of my peers at Columbia. He had a database of about 2,000 existing answers, assuming that since they all had to go through the same acceptance criteria to get into school, they had more or less, the same ability to give a good answer to this question. He went through and did some statistical analysis and basically took the norm answer across the various students at Columbia. So Andrew decided that as opposed to using his brain to give his individual subjective opinion on what the answer might be, he could instead crowdsource answers from all of the Columbia students who had taken the course in the past. So Andrew has what I like to call the AI instinct, which is to see a reasoning problem, his applying analogical and precedent-based reasoning in order to answer this question as a data problem, which is mimicking what looks like it would be the way in which we would encounter and answer a problem coming from the domain of analogical reasoning, coming from the domain of legal reasoning, whatever that may be, and turning it into a statistical exercise where, as Andrew did, he went through and looked across the distribution of answers from the past and then mimicked that into an answer. This was not always the case. So I was asked to talk about the history of AI. I figured we could go all the way back to Aristotle. 2 of the languages that I speak are dead, so please don't test me on my ability to speak Latin and Greek, but I can read them in a haphazard, somewhat shoddy way. And one of the reasons why I did that was because I really was keen to tap into the wisdom of the ancients, including Aristotle, who was famous for writing his Organon, which has some of the laws and rules of reasoning. So I'm sure everybody in the room is familiar with basic syllogisms, like all men are mortal, Socrates is a man, therefore Socrates is mortal. So there's this fabulous essay on the web by Chris Dixon, who's one of the partners at Andreessen Horowitz, where he describes and narrates the history of artificial intelligence going back to the ancients, claiming that Aristotle is indeed the real father of AI. So Aristotle, if you look at this syllogism, we tend to focus on sort of the nouns, right? So men and Socrates, et cetera. We could break it down and say, the words that are really doing the work here are all, are, is, and therefore. And we can say, okay, let's visualize this as sort of a mathematical problem where we've got the set of all men, and then we say, oh, look, Socrates is in that set, and everybody in that set, every element that's in it has this feature, namely that of being mortal, and therefore Socrates, because he's in there, should have that feature too. Right, so we turn what we sort of view linearly when it's presented as text, as a deductive problem, into something that's a little bit more like sets. So this guy, George Boole, in the late 19th century, who haphazardly is Jeff Hitton's great-great-grandfather, said, interesting, well, why don't we rewrite this notation algebraically? So we can go, all x is y, all y is z, therefore all x is z, and he says there's a way for us to represent that in formulations that could be more computable. I won't go into the notation there for the moment, but you can say, and this is what Boole did when he built out all these operators, we could think about one set, or we can think about overlapping sets. So things like, the set of Greek philosophers, the set of thinkers throughout history like Galileo who've been persecuted for having new ideas, and Socrates sits in the middle of these overlapping sets. And there's various ways in which we can sort of have sets interact with one another to reason about the world, or even define search problems, right? So you can think about if this and not that, and if this. So in the 1950s, Claude Shannon, building on Boole's work, said, oh, there's a way for us to represent this overlapping set logic in digital computational formats. That was a big break, right? This was the beginning of digital computers, where basically we have a series of gates. The gate can be up as a 1, down as a 0, and Shannon's real breakthrough in early information theory was to transform these logical operations into sort of the physical material of gates going up and down. That, and many other things happened in between, led to some of the really interesting early developments in artificial intelligence. There's some other stuff that occurred in parallel, but for the moment, in terms of keeping in this narrative, there was the rise of what we called expert systems in the 1980s, where we said, okay, well, we can actually compound upon the types of reasoning that we might capture in the rules within these digital gates. So expert systems are systems wherein somebody knows a lot about some subject matter, let's go back to law, and they can basically transform their subject matter expertise into a set of if-then type rules that can be encoded into a system that a user then interacts with. So it's basically baking knowledge into systems in a sequence of determined rules. What's shifting in this new AI moment is, I think Jeff Bezos does a really good job capturing this in his 2017 letter to shareholders, is that we're moving from the types of tasks, the types of logical operations that can be encoded very well in hard rules, that map that syllogistic logic that goes all the way back to Aristotle, into a world where we can automate processes or we can describe knowledge in the world where the rules are much more fuzzy. Aristotle, for that matter, actually had, alongside the organon, he tried to describe the truth that's told when we predict events in the future, and he fumbled. It led to a second branch in logic that was much more probabilistic, and that actually is behind some of this rise here. So this is a big shift, and it's basically one where we're moving from thinking about using computers to automate tasks that seem to be intelligent in a way that requires formal rules to ones where we're basically inducing knowledge out of vast domains of data. I used to work at a company called Fast Forward Labs, and my colleague Hilary Mason had built out what we like to think of as the Maslow's hierarchy of data science capabilities. So at the foundation of this new fuzzy world that Jeff Bezos describes lies what, for lack of a better word, we call big data. This term is often abused and overused in the literature, but it basically is the ability to collect, store, and process data at scale. And then we say, okay, so now that we have all this data, how can we think with it? How might we process it to do stuff? The first level of capacity is analytics. So this is performing sort of basic operations on data, like adding, subtracting, multiplying, so that we can understand what happened in the past quantitatively to help make qualitative decisions in the future. When we go on to data science, we basically shift from counting to doing a little bit more complex mathematical operations. So we can, for example, make a linear regression, so plot a bunch of data points, see a trend line, and then use that trend line to make quantitative predictions about what might happen, as opposed to just looking at the past to inform qualitative decisions. When we go into machine learning, we get feedback loops. So as opposed to just plotting a function, as we get new data, we can learn that function. Learn is a term of art that basically means our slope changes. And that slope can go from being linear to being super complex and projected out, not in the measly 3-dimensional space that we think in, 4 dimensions if we include time, but also 50 million dimensional space. And Geoffrey Hinton might be able to sort of have intuitions about what it feels like to be in 50 million dimension space, but the rest of us mere mortals can't. And then AI, I consider it to be sort of a marketing term these days. Sean started off by talking about this discrepancy between hype and sort of deep science. Even people within the field disagree on what it means. I like to think about it as whatever computers can't do until they can, right? Because this domain of technology is shifting so quickly that it's hard for us to define rigorous categories of what qualifies as AI and what doesn't. Where Google Maps, as an example, is a tool that for us has become just plain old software, although it's powered by the same sophisticated data and machine learning algorithms as, say, are going to appear in self-driving cars. This shift is remarkable in terms of the types of capabilities that it's opening up. So if we look through the developments that have happened recently in the domain of natural language processing, the Aristotelian version of the world, this also influenced by thinkers like Noam Chomsky, is one where we start off with a complex domain of data, like language, which has nuances, right? There's differences in dialects. There's all of the jargon that we come to easily assimilate on a day-to-day basis. In early techniques, we would say, we need to take this mess and turn it into something that can be represented as those 0 and 1 digits in a database. So early techniques would be to sort of break down a sentence into component parts, represent those component parts in sort of a database-like structure, and then try to do analysis thereupon to make meaning from computation. In the early 2000s, we shifted into a world where we had much more data in the early big data age, and we sort of turned these NLP-like problems into statistical problems, where if we were to do something like try to develop an automated translation system, we'd have tons of examples of a sentence in English and tons of examples of a sentence in French, and sort of turn this translation problem into a lookup problem in a database. Today, in the big shifts that are occurring in the space of deep learning, which Graham will talk about in a minute, we've gone from using our minds to break things down into seemingly computable components to allowing the system to embrace the richness and mess of what exists in complex data sets. So contemporary natural language processing techniques will start us with a sentence, represent it as a vector, which is a string of numbers pushed out somewhere in this 50 million dimensional space, and then use the geometric properties between different aspects of language as proxies for meaning. So a great example there is these word analogies, where we've seen some systems where you can input man and input woman and trace the distance between the two, input king and say, as man is to woman, so king is to what? And the system will use basically just the curvature in space and say, up, it's queen, and get the right answer. Skip over this slide. This same sort of technique in moving from a rules-based deterministic world to one that's much more probabilistic is having impacts across various application domains. So example from the domain of cybersecurity, 10 years ago, in order to catch the bad guys, you needed to have a sacrificial lamb. So some company needed to have been hacked for companies like Symantec or McAfee to get a trace of whatever that malware code was and then update their code base for other organizations so that they didn't get hacked by the same bad guy. Today, companies like Cylance say, well, malware, there might be differences between different pieces of malware, but they're not all that different. They evolve in a way that, as Quade Morris at the Morris Lab and Vector Institute would say, is actually quite similar to the way cancer cells evolve. So if we can understand this evolution, we can probabilistically predict what the bad guys might do next and then catch them before somebody actually gets hacked. This is having implications in the domain of marketing and product suggestions. So we're probably by now familiar with Amazon and Netflix and recommender systems where each of us experience something different when we go on the internet as regards to the types of music that were recommended or the products that companies think are interesting for us. So in the early 2000s, the standard technique behind recommender systems was something called collaborative filtering, where Sean and I would go on Amazon. They would use our past purchasing history, so a sequence of transactions to understand that we were lookalikes, so that, if Sean goes in and he buys a food processor, an espresso machine, and some spice grinders, and I go in and I buy 2 of those items as well, they'll say, let's recommend Kathryn the last thing that Sean bought as her next purchase, because they seem to be quite similar. So this worked quite well, but has limitations because you have to have data about people's past purchasing behavior in order to make those kind of comparisons. So the new techniques that are coming out in AI enable us to shift from 2 people act like one another to this person might have affinities with a product. That requires our ability to not only work with transactional data, but work with rich data like images and videos and text, where we can sort of develop, again, a mathematical representation of a product, a mathematical representation of a person, and try to see that those 2 things are similar. Last example here, it's hard to see a little bit with the light, but we're also shifting into the realm of hyper-personal recommender systems where one can use convolutional neural nets, which Graham will talk about, to sort of parse out somebody's age and skin type from a mere photo, and then use that to recommend the best product mix for beauty products or whatever that may be. What's interesting about this example is while it seems a little bit creepy, right, in terms of a privacy perspective, to have a system that can automatically do facial recognition and identify your age and skin type, it actually doesn't require that we share data and do data mining to find contrast between two different people. So it's actually a much more privacy-preserving technique if the organization has the ethical policy level to not then share these profiles with others. So why is this occurring now? A lot of these algorithmic techniques that are behind the so-called deep learning evolution date back to the 1950s. This is an example of the first neural network. It was a hardware neural network with a bunch of wires connected together called a perceptron in 1957 by Frank Rosenblatt at Cornell. In 1993, I love this video online, Jan LeCun and Jeff Hinton had done some work in the 1980s applying these to make one of the first neural network applications, which was the ability to figure out numbers on checks, which led to the ATM machine as we know it. So actually, the AI evolution, the AI revolution and its impact on how we engage with society has been going on for quite a while. In the 1980s here in Toronto, Jeff Hinton made a very big breakthrough in taking the architecture of these systems that were able to induce mathematical rules as opposed to hard code them, and he modified the math a little bit so that they could learn from examples and get better over time, which really catapulted the algorithm's capabilities, but what they lacked was data, so enough data to be able to induce those rules and not require human input. They lacked the right hardware to really scale this math in a way that was able to train these algorithms quickly so that they became practically feasible as opposed to taking months and even years to train. And they lacked the right open source community to shift this from being the pet project of a couple of academics into something that really had widespread applicability across the startup and enterprise ecosystem. So last note, before I pass it on to Graham, in terms of where we are today and what kind of applications we're going to see over the next couple of years. There's a distinction in the community between what we call narrow AI and general and strong AI. So narrow AI is the ability to build systems that can complete one task really well. An example of that might be the ability to automatically discern using a system whether or not a brain is cancerous or a lung has pneumonia. This seems to us like hyper-intelligent activity, but that requires a lot of professional development and skills. But it's a very narrow task that can be automated using a set of examples. Contrast that with strong AI, the ability to sort of discern common sense and reason across applications. So something that seems very easy for us, like getting up and brushing our teeth and tying our shoes and driving our car to work, would be extremely difficult to automate. So it's easier to do one narrow and yet seemingly super intelligent task than it is to do many. This means that over the next couple of years, we're going to continue to see a sort of hot mess of various startups and applications. There's a ton of startups that are out there. They often are solving very narrow problems in a very focused domain, as opposed to having hyper-intelligent general solutions that can change things at scale. And the last point I'd like to make in terms of sort of where things stand and what this means as you're thinking about it, that prefaces some of the ethical comments that we'll see later on today, is that the big shift in AI product development as we start to use statistics to power decisions and to power actions that we take in the world is we're moving from the realm of passive analysis. We've done sociological analysis on trends in society for years, to a place where we bake what was statistical observation into a product. So we have to transform these distributions into some mechanism for action and have a feedback loop that can then impact what these distributions tell us. That's really important in that if we take an example of conviction rates across different socioeconomic classes in various jurisdictions. In the past, we used to study these trends. Now we're baking these trends into principles for decisions and then acting on them at scale. I think it's an extremely important thing to keep in mind as we consider some of the ethical and policy obligations. Last thing I want to say, and there's a ton of talk and people are keen to know where this is going to go in the future. We don't know. It's very hard for us to predict, and we tend to imagine things based on what we see today as opposed to where things might go in the future. There's a great set of cartoons from the late 19th century where a French artist depict the year in 2000, and in a completely parochial and adorable way, sort of depicts what it's going to look like to be Google in the 20th century, where you have these machines that are impacting information into students' minds.